Okay, ladies and gentlemen, final section of the chapter, and it's going to be a law of sines, law of cosines. Now, the good news is you should have already had law of sines and law of cosines, both a little bit in geometry, but also in algebra 2. So this should be primarily review for you. In this case, the law of sines is sine A over A. Now, the big A, of course, meaning angle, little a, of course, meaning side, equals sine B over B equals sine C over C. Now, of course, at any one time, you're not going to use all three parts of that. You're going to use any two parts. So you'd use sine B over B equals sine C over C, or you might use sine A over A equals sine C over C, or you might do that combo, but you're not going to use all three at once, but they are indeed all three equal. So you have a proportional relationship. Now, of course, you can flip them over. You can put the side on the top and the angle on the bottom, side on the top, angle on the bottom. What you can't do is you can't mix the two. Whatever you do with one, you have to do with the other. Now, law of cosines. Side A squared equals side B squared plus side C squared minus 2 times side B times side C cosine of A. So you have the side and the angle opposite that side have to be on the very ends. It can't be in the middle. Now you could set B as its piece by itself as long as you put B at the back. C is by itself as long as you put C at the back. So these are your basic laws of sines, laws of cosines. Shouldn't be a challenge. Here's the situations in which you use them all. Now let's go put our back way into geometry. And if we go way back into geometry, we know that we can prove triangles congruent by side, side, side. Because if I know three sides of any two triangles, those sides are congruent. If I have the side, an angle in the middle, and a side over here of any two triangles, we know those two triangles are congruent. So we use basically that same format, and we can come up with all of the different ways to start solving. Now, we're going to use laws of cosines over here, because obviously law of cosines involves all three sides at once. Well, if I can involve all three sides at once, side, 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 then the only thing I don't know is the missing angle. And I can do it right there. If, on the other hand, I have side, angle, side. Now you say, well, I have sides and angles over here. Well, that's true. But over here, the law of sines requires you know an angle and the side opposite that angle. The angle and the side opposite that angle. I don't have an angle and a side opposite. I have an angle but no side. I have no angle but I do have a side. I have a side but no angle. But in this case, I have no way of finding the remaining angle or the remaining sides. Why can't we use Pythagorean theorem? Well, because it's not a right triangle. How come we can't use sine and cosines and just solve them like that? Not a right triangle. So in all cases, we have these different rules that we're going to have to put to use. In this case, I'm going to use, for example, if this were side X and then so this would be side Z, this would be side Y, I would say Z squared plus Y squared minus 2 ZY cosine of angle in the middle, which would be X. And then I could plug all that in, and it would spit me out the answer. Now, we have angle, side, angle. Angle here, side here, angle here. You'd say, well, wait a minute, you just said you have to have a side and an angle across from the side. I don't have that here. I have a side but no angle, an angle but no side, an angle but no side. But that's okay because I have two angles of a triangle, and therefore can automatically find the third side by using straight subtraction. So if I have 102 and if I have 24, that's 126. I do a little bit of subtraction, I come up with 54. Now I have a side and an angle across from a side. But down here, I have 105 and 12. They're already a pair. I have 31. All I have to do is find Z. And once I have that, I can find the third angle by a subtraction again. Find the missing piece. Now, the one that we can use sines and cosines for is the angle side side situation. Now we couldn't use angle side side in congruence because we weren't entirely sure what shape it was. And we have the same problem here. In this case, I've drawn one that we can be fairly definitive with. There is only one solution to this problem, so it is not ambiguous. But in other cases, we're going to have the same ambiguous problem that we had when we were proving triangles congruent. So, here's what I want you to do. I want you to do problem numbers 1, 2, 3, 4. Why is 5 no problem? And why do I have more than enough information there? Finally, I want you to do number 6. So, go ahead and do all of those, and then we'll talk about the ambiguous case. Okay, so now we come to the ambiguous case. Anytime using law of cosines, you're not going to have to worry about it. Anytime you have a right triangle, you're not going to have to worry about it. Anytime that you have a law of sines where you have angle side angle, you don't need to worry about it. If you have an angle side situation, you don't have to worry about that because there is no ambiguity in the third side. However, if you're going to use law of sines in this case for the angle side, so again, just as in geometry, you're going to have to watch your angle side, because depending on the size of the sides and the size of the angle, you may have a situation such that, just like in geometry, you have an acute angle here, let's say 50 degrees for fun, and a side here, 6. And you have a third side that is long but not too long. It could come over here as 4. But then again, it could just as easily, using the same 6 and the same 50, kick back in like this at 4. Because I don't know the length of this side, so this side here could be quite long, or this side here could be quite short, and that's not part of the side at all. So I could either have an acute version of this angle, or I can have an obtuse version of this angle. I don't know which. Alright, that's why you have an ambiguous case. And so anytime we have something that we don't know for sure, the way we deal with it in math is that we actually find all possibilities. So one triangle problem turns into finding 2 triangle problems. The best way to think about this here is I have a side that could be kicked out like this, or if it's free swinging, swing around until it hooks up in here and it looks like this. So I have 2 different possibilities. Now, the book does include a very nice little chart, and it says if A is a right angle or an obtuse triangle, and as long as A is bigger than B, in this case A is bigger than B, you have a triangle. If A isn't bigger than B, then guess what? You don't have a triangle. So it's not that challenging in the case of a right or an obtuse, because it either is big enough or it's not big enough, so it either will work or it won't work. However, if it's acute, if I have my same 50 degrees and I have my same 6, if I have a little side of 1 here, it doesn't matter whether it's kicked in like this or here or here or here, it's never going to be long enough to reach all the way down to the bottom. So it does not make a triangle. If, on the other hand, I have this 6, and I have this 50, and I have a triangle that is just long enough, has a side that's just long enough to make the opposite side and the angle 90, that's a possibility. It could make exactly 90 over here. And that's going to be one possible solution. Okay? If, on the other hand, I give you a situation like I did over here, where the other side is way bigger than the first side, there's only one way for it to touch, because it touches way out here, but if I try flipping it around, it's never going to come back and touch, and it's just going to go out and be the same thing on the other side. So, in this case, I don't have to worry about it, because A, the opposite side, is way bigger than B. It's where A is less than B, and it's also less than a hypotenuse, something that makes it right, that we have a problem. And that's the case where we have 2 solutions. Now, in this case, let's see if we have potential for two solutions. Do we have an acute angle? Yes. Okay, so we're up here on the top row. Is the side opposite that angle bigger than, equal to, or smaller than the other side? Well, it's smaller than. Well, the question is it too small? Well, I don't know. If I try it and I get no solution, that means it's going to be way too small. Now, looking at these numbers, we can say, no, that's definitely going to be big enough to get down to the bottom. So we're not too worried about that at this point. Now, is it exact? Well, if it were exact, we would be able to find it. Here we go. Let's find A over here. We would say sine of 50, because if this does happen to be right, I can now just use a straight up sine. A over 6. And so for it to be a right angle, I would have to have the following, times 6 times 6. 6 times sine of 50. Answer is 4.6. Schnooker. Because if this has to be 4.6 for it to be a right angle, what's true about our 4? Well, unfortunately, our 4 wouldn't be drawn to scale. Our 4 would come up short, and it would just hang here limply without ever getting to the side. So this, in this case, is a no solution. So it is shorter than 6, and it's not long enough to make a 90. So in this case, we would have no solution. What we'd be afraid of is if we have something like this. A 5. Now, is it acute? Yep. Is this side opposite, smaller than 6? Yes. But is it too long to make a perfect right angle? Yes. So now we have this situation where the 5 could kick out this way, or the 5 could kick in this way. And in that case, we have an ambiguous case. What we're going to need to do is solve both options. Now, to solve both options, we simply do the following. Split it into two problems. Split it into two problems. Let's do law of sines on this one. And it comes up with sine 50 over 5 equals sine x over 6. So, sine 50, enter, divide by 5, enter, times 6, enter, that gives me sine x equals 0.919, second sine, second answer, and that tells me I have a 66.8 degree angle. So in this case, 66.8 degree angle, or if that's the acute version, the obtuse version would be if I had 180 minus 66.8. So how do you find the angle in the other ambiguous triangle? You take 180 minus whatever the acute triangle is that you find, and that comes up with 113. So 113.2 is going to be this angle. Reason being, when I do an inverse sine, anytime I do an inverse sine, it's going to by default give me something between negative 90 and positive 90. It's not going to pick up an obtuse angle like that, so we have to change it manually from acute to obtuse. At this point, I can now find the remaining angle here and the remaining angle here. I can find the remaining side here and the remaining side here. And it splits into two different triangles. So that is the ambiguous case.